Centripetal. Centripetal. Center, right. Center seeking. Center seeking is what it means. So what it means is that the force is actually pulling this little roll of tape toward the center of the circle. How do you know that's the case? If I let go of the rope, that was good, right? If I let go of the rope, it continues. I let go of it when it was right here. It continues with its initial inertia, right? As it's circling around, so it'll keep going right at Hannah there. Does that make sense? The rope continues to pull it back toward the middle as it rotates around. Centripetal, center seeking. Does that make sense? Have you heard of another centri force, centra something? Gravity is definitely a force, but have you heard of another word that uses that center something? Centrifugal. Centrifugal or centrifugal force. Have you heard of this before? It's actually not a force. In my hubris as a 19-year-old college freshman, I got into an argument with my high school physics teacher over this exact thing. We had a quiz bowl thing that they had going at the school. I went to visit my girlfriend who was there. And one of the questions, the answers was centrifugal force. And I'm like, but no, that's not really actually a force. Anyway, I was right. He was wrong. We're good. We're all right. I did. Shh, don't tell. Yeah, I did. Very kindly afterwards, of course, not like in front of everybody. But yes, so centrifugal force isn't actually a force, even though it's much more well-known than centripetal, right? Centrifugal is just inertia. It's just the effects of inertia. Think about, you've driven in the car with Tanner, I'm sure, right? You're going. I always pick on you, don't I? Sorry. And he turns hard, right? In that sweet truck that he has. When he turns hard to the left, what way does your body go? To the right, right? You smash into the door, right? Or, you know, if he's trying to get close to that certain somebody, he quickly turns the other direction and makes them fall over toward him, right? It's a slick driving moves. Nicely done. Okay? What you're seeing is that's inertia. That's that centrifugal force that people think throw them outward. It's not actually a force, it's just inertia. Does that make sense? So acceleration. What are the units for acceleration? Meters per second squared. Meters per second velocity, right? So because we're dealing with circular motion, we have a different... and what's our formula for acceleration that we know? Linear acceleration. Change in velocity over time. Meters per second squared, right? But this is what we have for centripetal acceleration is a different formula because we're dealing with circular motion, right? So we can't just use the same formula again. Excuse me. And this is what we need to figure out how long, because the whole point of what we're doing here is we want to simulate the amount of acceleration your rockets will undergo. 20 Gs. So about 200 meters per second squared is what we're trying to simulate, right? So we need to know, if I want to spin this thing, how long does my rope here have to be in order to get 200 meters per second squared? Does that make sense? That's the whole point with what we're doing here. So here's our acceleration equation. You take velocity squared and you divide it by the radius of your circle. Let's look at the units. What's the units for velocity? Meters per second. So if I square it, I got meters squared over seconds squared, right? And if I divide that by radius, what units would radius be in? Meters. If I divide meters per second squared, meters squared, second squared, divided by meters, are you comfortable? That just gets rid of that. And now I have meters per second squared. That's acceleration. Does that make sense? I just wanted you to see, even though it looks totally different than our normal equation for acceleration, we still get the same units. So, how do I calculate velocity? Radius is pretty easy, right? Just the length of our rope. How do I calculate velocity? Okay, final initial what? That would be change in velocity, sure. But what would velocity itself be made up of? Distance divided by time, right? Meters per second. And I think that I put them as multiplied, didn't I? I did. Mr. Hess is not awake when I was doing this. My apologies. So it's going to be distance divided by our time. Whew, man, I was tired. I was doing this really quick because I couldn't find I already did it once, and I couldn't find it. Distance divided by time. Meters per second. Are we cool? If I want to find velocity. My distance is going to be my circumference, right? The circumference of the circle is going to be the distance. Again, if I'm spinning this guy, right? I'm spinning, right? My circumference of the circle I'm creating is how far that tape goes each time I spin it. Does that make sense? Are we cool? All right. So therefore, if I want to find circumference, what's my equation to find circumference? Do you remember? 2 pi r, or diameter times pi, right? Good. So circumference 2 pi r. So let's put all these guys together into just one equation to find centripetal acceleration. So it's going to look like this. And I have my t on the wrong side because it's going to be divided, not multiplied. Are you with me? I just simply took all of those things and combined them into one something. Okay? So our goal is 200 meters per second squared. That's what I want to know. That's what we want to get. So my question is, how long does my r have to be to make that work? Does that make sense? I'm going to give you a way to make this a slight bit easier. Let's say that we are going to make our time 1 second. So in other words, to go all the way around one time, let's make it 1 second. It'll actually end up being probably a little bit longer than that, depending on how long you see your rope is, but we'll keep it at 1 second. It just makes your calculations easier. Does that make sense? So if you want to go even more specific, it'd be 1 hertz, right? There's a rotation or a frequency per second. That's what we've got there. And this is about 1 hertz going around. Are we cool? So this is really what I want you to spend some time with in your group. Using the equation, how can we, what length does that r have to be? I would encourage you, what I did was I used, just on Google, pop in circumference of a circle formula, and you can enter values here and get your C. If you have another calculator, you could even plug in the whole equation and just add different numbers to it. Again, I'll leave that for you guys. You can work it out on hand. That's fine. What I'm looking for is a number. What is a number that you think the length of this rope should be? And again, backed up by your calculations to show me that. So it really doesn't. It makes it more effort for you to get it going and keep it going? Yes. Yes. But we're not looking for force, we're looking for acceleration. So you're correct. If we were measuring force, then yes, the mass of it, I have to have more force to get the same acceleration. You're correct. Does that make sense? But we're not looking at force, we're just looking at acceleration. Good question. Are you comfortable here? All right. Again, please in your groups. I want you to work on a number here for us. I'm assuming everybody turned in your piece for today, the results from yesterday? I didn't actually look yet. Uh-huh.
If you told us in class or you put on school, there's one day we had homework, but then the next day you said if you didn't finish it, you could come turn it in.
Uh-huh.
Did you look for that yesterday? Like check for it?
I assumed if you did it, you were going to come give it to me. I had a couple of folks who did that. But no, I did not ask you for it, no. I did not. If you had it done and you didn't bring it to me yesterday?
Yeah, I got distracted with coal drops.
Thank you. Oh. And I apologize, there is another squared here, by the way. Because again, it's velocity squared, and that t is part of velocity, so I want to make sure you saw that that was a square there as well. Radius. Uh-huh. Yep. You could have put it up here and go squared. I can do that, if that would make it easier. Do you like that better? I find that to be easiest. You don't have to if you want to do a slower, but it's tough to keep. Once you get long enough, it's tough to keep it going at much less than that. Uh-huh. I want you to get 200 meters per second squared. That's our goal for acceleration. And I want to know how long does the R have to be? How long does the rope have to be? You can also just kind of trial and error the length and see what you think. You can do it either way. But if you're gonna rearrange the equation, yes, 200 is your A. That's your acceleration.
5.08.
Meters. Pretty solid. Mm-hmm. No, you're done, eh? What you got? Sounds good to me. Sounds good to me. Sorry, I forgot I'm still recording.